right. Hi, everybody. So, just wanted to add a supplement to our Hohmann transfer math video. In that video, which is great, it is not the whole story. Or rather, it's the whole story of one type of story. we want to add another situation that you could possibly consider with a Hohmann transfer. So, having said that, I want to introduce to you another possible scenario. So, in the previous video, we talked about going from a circular orbit to another circular orbit with a Hohmann transfer. And that's true. That's a good thing. That is a use of a Hohmann transfer. But also, you might find yourself in an elliptical orbit trying to go to a circle, or a circular orbit trying to go to an ellipse, or even an ellipse to an ellipse. And what I'd like to do is just prove here that the process that we introduced in the Hohmann transfer circle-to-circle video is exactly the same process that you would use for an ellipse to an ellipse. The equations are even the same equations, generally speaking. You're just going to have to keep kind of careful track of which A and which R. That's where you make your money with Hohmann transfers. So, having said that, I give you an example of picking the wrong color. That's what I'm giving you an example of. I want to do red. So, let's do a Hohmann transfer. I abbreviate it TX. But we'll do ellipse to ellipse. And again, I'm going to try and prove, hopefully you'll buy it at the end of this video, that you'll buy the fact that the math is the same. It just becomes a little harder to visualize for some reason because, honestly, ellipse to ellipse has some more complexity. So, okay, so let's say, let's see, this is my scratch paper in my upper left here. I'm going to draw us kind of a, let's make the Earth black. I'm very excited. I just learned how to draw perfect circles with my iPad pencil today. A cadet taught me that, so shout out to them. Thank you. So let's say this is the Earth, and let's say we're looking down at the top of it, right? And I always draw a polar ice cap, so I know I'm looking straight down at the Earth, and that little dot is K-hat pointing out of the screen at you. Okay, and so let's start off. Not only we're going to basically do everything differently than the previous video. We had two perfect circles, and we were going from one perfect circle to another. We were going from small to big, and that was very intuitive. All right, so let's not be intuitive, and let's flip everything on its head. Here's what I want to do. I want to start off with let's see. Yeah, I'm going to start off with blue. And let's say we're in a very elliptical type of orbit that is, let's see, oh, sweet. Technically, this is called a tundra orbit, the kind of orbit that I'm about to introduce to you. Sirius XM satellites used to be in this. I think they're now in geostationary, but old Sirius XM satellites, they launched into what they call a tundra orbit, and it has a 24-hour period, but it's highly inclined. So I'll give you the introductory conditions here. So starting off orbit will be, I'll have a semimajor axis of actually the same as geostationary, but it's not. It's very eccentric by comparison. My ellipse might not match that exact. My drawing might not match that, but that's okay. And it has the inclination of a Molniya orbit, which is whatever. Now let's say that I was Sirius XM and I was ready to get rid of these satellites one by one and help them deorbit so that they don't cause space junk. And let's say that our second orbit is going to be real close into the Earth here. In fact, it's going to be so low that within a few orbits, max a day or two, when it enters that second orbit, it's going to burn up in the atmosphere. That's often how we dispose of satellites that are at the end of their lives. So, yeah, I'm contriving the scenario a little bit, but stick with me. It's really just for the sake of the example problem. So let's say our orbit 2, which is red, and I really am going to try and color code things as much as I can because I find that to be helpful. I'm a visual kind of a learner. Orbit 2 has the properties of being, let's say I give you the altitude to be even more tricky. And I say we're going to have 125 kilometer orbit because, as you guys know, space starts at a right about around that altitude. So, and let's not make it a perfect circle. Let's make it like eccentricity of 0.1. And we'll say, because we're in a Hohmann transfer lesson here, we're going to make the inclination the exact same. Otherwise, we'd have to do a plane change, and that is a story for another time. So we're going to say that we're not changing inclination. We're just going from big orbit to small orbit. And not only that, let's see. Let's say we want to burn from, let's see. Let's say I want to go from perigee of my transfer orbit say the question asks you what's the delta V total to go from perigee, I should say of the mission orbit, sorry, to, let's flip everything on its head, to the apogee of what we call the disposal orbit. So I'm going to use terms like mission orbit and disposal orbit because that's what a problem would give you. But mission orbit is what a satellite spends most of its life in doing its mission, duh. And the disposal orbit's that small orbit that's going to basically pull it out of, due to drag, right? This is the Earth. I'll make sure I color this in so you know what I'm looking at here. It's going to, due to atmospheric drag, it's going to lose a lot of energy from its orbit very quickly and burn up in the atmosphere. Okay, cool. So that's what the problem wants to know. What's the total delta V? And of course, as always, it'll ask for what's the time of flight of that. So in my contrived, very contrived problem here, I'm going to do basically a maneuver that gets me from perigee, hopefully you guys would buy that this is perigee of this blue mission orbit, all the way, oh boy, to, oh nice, there we go, to, let's see, maybe I can do a little bit better on that. Drawing, always a challenge. Ah, there we go. Yeah, to apogee of the secondary orbit. And again, this, you can barely tell, right? This red orbit looks almost like a circle, but the problem tells us it's not quite a circle. It's a small eccentricity, very small, right? But still an ellipse of some kind. So we want to go from, and as you can see, if you really zoom in, like this point here is a little bit farther away than perigee of this disposal orbit. So, all right, so we have all kinds of like contravening factors going on. Not contravening, but conflicting, if you will, factors. We've got two elliptical orbits, and we're not just going perigee to perigee or apogee to apogee. We're going perigee to apogee of a smaller orbit. It's literally, it could not be more different than the previous video's scenario. But I'm going to argue that the math is truly, truly the same. So what do I mean by that? Okay, keeping with my color coding, let's come down here. Let's think about, we're going to have to take some math and find out how fast we're going before we do our burn. We're going to do a burn that'll slow us down somewhat. It'll bleed off some energy from our blue orbit and put us in the transfer orbit. We'll do a second burn after we reach our inner disposal orbit. And then we're at that point, we're going to be going a certain final velocity after that. Okay, in my previous video, we had the luxury, and it is a luxury, of having circular orbits at the ends, both ends of the transfer orbit. So we could use the v-circ equation from the equation sheet. That's not the case here. We're going to have to use elliptical equation for every single velocity. Now, what I'll tell you is that this approach always works. So if you were to say to yourself, you know, I'm going from a circle to a circle, and that's wonderful. I am not sure if I remember the math correctly. I'll just use the ellipse equation for each velocity. That will work. That will always work. However, in this case, we're forced to do it because we're going from an ellipse, entering a transfer orbit, which is an ellipse, and going to a final ellipse. It's almost a circle, but not quite, so still it's technically an ellipse. So basically, we're going to really have to, let's zoom in here. We're going to make a lot of money as far as using this. Like, we're going to make all our money using the elliptical equation is what I'm trying to say. So, in its general form, this is the velocity of how fast you're going in an elliptical orbit. Square root of 2 times quantity mu over r plus epsilon. But the trick is which r and which epsilon. Okay. It's really important, this is my approach, but that you understand where in the story you are. All right, at V1, let's say our satellite's going counterclockwise. And it's happily going around its orbit. Oh man, it's really slowing down because apogee, as you guys know, oh man, it's like a lot slower than perigee. Okay, so I'm being silly, but it's going counterclockwise. And then the Space Force folks that are operating the satellite, or the company operators, I forget, let's just call it a Sirius XM satellite. The company operators are going to do a burn, and they're going to do a burn to take it from blue to red. Okay, so from the big elliptical orbit to the small elliptical orbit. And that burn is going to take place right at this green X. X marks the spot in Astro and in Pirate Treasure, because Astro is as valuable as Pirate Treasure. See what I did there? And then, of course, we'll enter that transfer orbit, and then we'll do another burn over here at this other green X that marks the spot. Just like Jack Sparrow. Just like Mr. Jack Sparrow, Captain Jack Sparrow. Okay. All right. Not trying to do a plug for Pirates of the Caribbean. Just whenever I'm marking X's on a piece of paper, I feel like I'm making a treasure map, you know? So, okay. Right now, before we do the burn, at this location right here, we're going to be going a certain speed. We haven't entered the transfer orbit yet. We haven't done a burn yet. So it's the speed of where we are basically at perigee of this mission orbit. Okay, and the reason I say that, that's actually very important. So what this is going to be is the problem told us we're going to burn from perigee of the mission orbit. So that is our dead giveaway. We're going to use, from the equation sheet, r sub p, a times 1 minus e. And that's going to be our r, because right before the burn occurs, that's where we are. We're at perigee of our mission orbit. And then epsilon, well, this is interesting, actually. Epsilon is going to be negative mu over 2a for all 4 of these velocities. But the trick is it's going to be different by which a we use. All right now, we're still in the blue mission orbit, which is a tundra orbit. And the problem told us the Semimajor axis of that bad boy is 42,164 kilometers. So that's the a we're going to use when we plug this in. All right. Because we're still in that ellipse. We're still in that ellipse, and we need to do that. So, and then, of course, perigee here. This equation, we'll do a little plug and chug. So that's what's going to go in there. Okay, so let's do plug in the values and see what we get there. Okay, let's see. 42,164. Okay, that ends up being 25,298.4 minus, I'm going to zoom in a little more even, 398600.5 over 2 times a, which again, a is 42,164, because we haven't entered the transfer orbit yet. Still in the first ellipse. Now we get to do mathematics, which is always fun. Which are always fun? Yeah. Subject-verb agreement, always important. Times 2, square root of that. Okay, so before all this kicks off, I get that we're going about 4.697 kilometers per second. Okay, sweet. It's a big orbit, so it does make sense that perigee is going not as fast as you would imagine. Not super fast. Certainly not as fast as the Leo orbit. But man, we're going to be going fast, that's for sure. Okay. Now, time to think about VT1. Okay. Guess what? We're using the same equation. But we're going to plug in different things. mu over r plus epsilon. Still confident with that. But which r are we going to use? Well, as soon as we do our burn, VT1 is the speed right after we do our burn, our first burn. So we haven't moved. We're still at r sub perigee of the mission orbit, but we've added a bunch of, well, actually we've bled off a bunch of energy from our orbit. And so the difference now is with epsilon. And again, you make your money here by remembering where in the story you are. So at this point at VT1, we've just done our burn. So that means we're no longer in the A of the mission orbit, and I'm going to label this A sub m up here. We're going to be in Semimajor axis of the transfer orbit. And you might say to yourself, well, okay, this is something we're going to have to do up here. What is the Semimajor axis of the transfer orbit? It's the two Semimajor axes. Well, no, I shouldn't say that. It's the two. It's the starting point and the end point average. So here's what I mean by that. We're going to take the distance from center of the Earth out to here where we did our first burn, and we're going to take the distance between the center of the Earth to where we're about to do our second burn, and we're going to average those two things. That's what is going to make up the Semimajor axis of the transfer orbit. So the problem says we're going to do our first burn at r sub perigee, and I'm even going to put submission orbit there. And we're going to end at apogee of the disposal orbit. Or divide those by 2. Okay, so we do know part of this. We found out what the perigee of the mission orbit was. That was 25,298.4. We don't know yet what the apogee of the disposal orbit is, but I bet you we have an equation for it, right? A times 1 plus E, right? Apogee. That's the radius of apogee of any particular orbit. And they tell us that at apogee, this is what makes this a little complicated. At apogee, the altitude of this bad boy is 125 kilometers. And so at apogee, it's 125 plus the radius of the Earth. And I guess I should have been a little more specific here. The altitude when it arrives on satellite arrives in orbit will be 125 kilometers. And so that's what we're going to put in here. All right, back to using green. So what does this come out to be? Let's see. 25,298.4 plus. So let's see, 6378.137 plus 125. Okay, I'm going to divide that all by 2, so I get 15900.7685 kilometers. All right. That was us taking perigee of the mission orbit, which is right there, and averaging it with apogee of the disposal orbit, which is over there. Because that makes up the two starting and ending points, essentially, of the transfer orbit. Ta-da! All right, now let's go back to work, because this is what goes in here. So now it's time to plug and chug, as we do. Let's zoom in. Okay. So we take the square root, 2 times 398,600.5 over radius of perigee, which remains unchanged. We've just done our first burn. We haven't actually moved yet, because remember, our assumption is these are instantaneous burns. Now we get to use our newly found transfer orbit, Semimajor Axis, 685. I have to keep extending my square root shape. Okay, so let's see how fast we're going after our first burn. Times 2 square root. Okay, so we're going 2.538 kilometers per second after our first burn. So, man, you can tell, like, we bled off some energy. Like, we started going 4.6-ish kilometers a second, and now, for that first burn, we're kind of dropping out of our mission orbit to go to a lower orbit. And so, because we are slowing ourselves down, we'll drop into a smaller orbit. Ironically, that's going to make us go faster. But if that seems mind-blowing, don't sweat it. Let's just work on the math here. Okay, so now in the story, we have solved for, let's see, we've covered V1. We covered VT1, like how fast we go after our first burn. And now we're following this path, this transfer orbit. And we spend however long, and we'll find out how long we spend in a second here, but we spend however many hours or minutes in this transfer orbit, and now it's time to do a second burn. And so we're looking for VT2. And of course, in a second here, we'll find how fast we're really going at that point. But one crisis at a time. Let's do VT2. Same equation as before. Mu over r plus epsilon. But which epsilon and which r, as always. Okay, where are we at in the story? Now we're at the point right before we're going to do our second burn, which is right here. And we're going a totally different speed than we were before. So what is that speed? We're a lot closer to the Earth now, so we're actually going to use r sub a, right, as we found out up here, right? R sub a of the mission orbit, a times 1 plus e, which the problem gave us, like, hey, when the satellite arrives in that final orbit, it'll be 125 kilometers above the Earth, so that means that r sub apogee is 125 plus the radius of the Earth. Easy day on that. So this is going to be r sub a. I'll make a different label for that. And then epsilon, since we haven't exited the transfer orbit yet, we haven't done our second burn, which means, let's say we didn't ever do our second burn. We'd be in a position where we'd be in that transfer orbit forever. We would just keep in this elliptical green orbit forever and ever and ever. So, or put it another way, we'd be, here, let's see if I can kind of help visualize it. If we didn't do our second burn, we'd be, ignore my imperfect shape, but we'd be in that kind of a teardropped orbit shape forever. We don't want that. We want to do a second burn so we can actually fully enter the red orbit. Okay, so this epsilon, what I'm trying to say is it's still that of the transfer orbit because we haven't done the second burn yet. We're right before the second burn. So somewhat mercifully, we now have all the numbers. Now we just have to plug and chug. Let's see here. Yep. 125 plus 6370. Sweet. 6503.137 minus over 2. Still that same semi-major axis of the transfer orbit because we haven't left it yet, technically. We haven't done our second burn. We haven't fixed our our orbit here. So now let's see how fast we're going to be going. I bet it's going to be a whole lot faster than our big mission orbit was because we've gotten a lot closer to the Earth. If I had to bet my mortgage, that's what I would probably say. Okay, cool. Yeah, so we are really screaming because right before we do this burn, we're going 9.875 kilometers per second. Yeah, we're going to have to definitely do a second thruster burn, right, and slow the heck down so that we can actually enter and be captured by, the Earth in its smaller disposal orbit. So, all right, so now let's say we do our burn, our second burn here to take us from VT2 to V2, because that's what burns sound like in my mind. Now we have to find out how fast we're going at apogee of the disposal orbit after our second burn. So now we've done our second burn. Unfortunately, we have no escape. We have to keep using the elliptical velocity equation. But now, which A and which epsilon? Okay, so we did our second burn. That didn't take us anywhere. We just basically changed the energy of our orbit. So this is still apogee of the disposal orbit. And I should probably list that that's disposal orbit 2. And then that's mission. I need to be careful with my variables, huh? There we go. Okay. So now let's see. We know what this is. This is that same value as before. I say before, same value as VT2. And this is the epsilon that is different because now we've added the energy, or rather we've bled off the energy we need to stay in the disposal orbit. So this is really A of the disposal orbit that we're going to use, and it's really not even that necessarily. It's specifically, no, that's right. I'm sorry. Yeah, I don't know why I'm telling you that. A of the disposal orbit. There you go. That's correct. Second guessed myself. Never do that. Never do that. All right. So now let's do a bit of... We're going to have to do a little reverse engineering. We haven't actually used the semi-major axis of the disposal orbit yet. And even worse, we weren't really given that. But we were given how high its apogee is. So we can do a little reverse engineering, which is exactly what we need. So we were told it's going to be 125 kilometers high as soon as it enters apogee of the disposal orbit. So that ends up being, let's see, 125 plus 6503.137 kilometers. We know that apogee of any old orbit is semi-major axis times 1 plus its eccentricity. We know the eccentricity of the disposal orbit is 0.1, so we can actually solve pretty quickly for what its semi-major axis is if we know how high its apogee is and what its eccentricity is. So we can let's solve this down. Rub-a-dub-dub. I don't know. It's just what you have to say when you're solving for semi-major axes. Say rub-a-dub-dub. I don't make the rules. So let's do that, and let's see. All right, so it's semi-major axis, which makes sense. It's a little bit smaller than its apogee because it's elliptical, 943 kilometers. All right, now we get to use that down here. Finally, in epsilon. So let's plug and chug all our numbers. We're getting there. We're almost there. There and back again. An orbit's tail. Okay, so 6503.137. That's our apogee of the disposal orbit. Minus 2 times the semi-major axis of the disposal orbit, which they were cruel enough to not give us, but we overcame. Just like Bear Grylls, we adapted and overcame and reverse engineered it ourselves because they did give us everything we needed, just not in a delicious, easy form. That's okay. So now doing a bit of plugging and chugging. Minus that. All right, so after we've done that second burn and bled off some of the energy of that very fast transfer orbit, we're going 7.427 kilometers a second. Okay, so in summary, so far, what we've done is we found out how fast before the burn, how fast after the burn, how fast after the second burn, how fast before the second burn, how fast after the second burn. Sorry. Okay, excellent. Now we're really to the easy part now. So let's find out what delta V1 is. Let's find out what delta V2 is. Then we can add them up and be done with this problem. My goodness gracious. Okay, so delta V1, as your equation sheet tells you, is the absolute value difference between how fast you're going before the first burn and how fast you're going after. And that holds true as far as process goes for delta V2. All right, so we'll plug and chug now. V1 before the burn was 4.697. And then we're going to subtract out how fast we're going after the burn, which is 2.538. And that is what? 4. Oh, that's not a 1, by the way. That's supposed to be the absolute value symbol. So that gives us 2.159 kilometers a second. That's quite a bit of delta V. Okay, V2, 7.427 minus V transfer right before we do the second burn, which is 9.875. All right, let's see here. 7.427 minus 9.875. Absolute value of 2.448 kilometers a second. All right, the total delta V is those two added up. So that 2.448 minus 2.159, 4.607 kilometers per second is delta V total. We did it. Ta-da! Okay, sweet. Now, there was one more thing it asked for, and that was time of flight. So let's address that right quick. I'll zoom in here and try and fit it all in one place. You guys have the period equation, because that's the time it takes for one full orbit. But when I'm asking about time of flight for a Hohmann transfer, I'm saying how much time do we spend in the green orbit? And that's only half an orbit, unless the thrusters don't fire on the second burn, and then you're kind of stuck in that transfer orbit forever. But let's say everything went correctly. So I guess what I mean is when everything goes correctly, your time of flight for a Hohmann transfer is half of a full period. So if I divide the period equation by 2, that cuts out the 2 pi and just makes it pi times a cubed over mu. Now, in keeping with my color coding, which A are we asking about? Well, which orbit are we asking about? Time of flight has to do with the transfer orbit. So we're going to use the A of the transfer orbit, which we found was 15,900 point, let's see if I can remember it, 7685. So 15,900.7685. Running a little low on space, but that's okay. No pun intended. Cube there. So this will be, come on, pi times 15900.7685 cubed over mu. This is going to come out in seconds. Okay, so I get that it comes out to 9977.187 seconds. And I, off the top of my head, don't know really how much that is because it's a large number of seconds. So I'm going to divide by 3600 to tell me how many hours that is. Maybe that'll give me a better intuitive sense. And I get that's about 2.77 hours. So we're going to spend almost 3 hours in the transfer orbit. Okay. Woo! We've come a long way. So what do we do? Well, first of all, we kind of had to find out how fast we're going before we burn, how fast we're going after we burn, how fast we're going before the second burn, and then how fast we're going after the second burn. And again, we had to use ellipse velocity equations for each of those. And the trick is keeping track of which R and which A we're using, right? Which R we're using and then which A for the epsilon are we using. And then the rest falls pretty quickly into place, right? The delta V1 is found the same way as the previous, example, and delta V2 also found the same way, as is the time of flight. So